Okay guys, welcome to our final video for the unit of bonding and molecular structure. We are going to be looking at substandard C.3.6 to use structural formulas of hydrocarbons to illustrate carbon's ability to form single and multiple bonds within a molecule. What are hydrocarbons? Hydrocarbons are compounds composed of hydrogens and carbons only. Organic chemistry studies carbon chemistry exclusively, and therefore hydrocarbons are very popular reactions to study. Hydrocarbons in the petroleum industry. Most of the wars between the United States and the Middle East is over control of hydrocarbons. These hydrocarbons are petroleum, gas, and oil deposits from super dead and super old sea creatures decomposed and buried by geological activity for thousands of years. Hydrocarbons can form single, double, and triple bonds. Because of their unique chemical and physical properties, hydrocarbons are valuable to extract energy from in the form of combustion reactions. Carbon and hydrogen are both critical elements to all life as we understand it. An example of a combustion reaction from a hydrocarbon would be when you get in the car and you turn the key over and the gas is being used to create energy. What happens in that combustion reaction is that you have the carbons and hydrogens which are separating into carbon dioxide and water molecules. Types of hydrocarbons. Hydrocarbons are organic compounds composed of carbon and hydrogen only. For example, methane, CH4, ethane, C.2.H.6, propane, C.3.H.8, and propene, C.3.H.6. Now glucose, C.6H12O6, has the element oxygen, in addition to carbon and hydrogen. Because the oxygen is there, it's not a hydrocarbon. Hydrocarbons are exclusively composed of carbon and hydrogens. Hydrocarbons are divided into two main groups, namely aliphatic and aromatic compounds. These are further divided into subgroups as shown below. So we have the overarching hydrocarbons, aliphatic hydrocarbons, and aromatic hydrocarbons. In order to be aromatic, you have to have single and double bonds which are alternating. If you're aliphatic, if it's an aliphatic compound, it does not have double and single bonds alternating. Aliphatic hydrocarbons. Okay, so this did not show up properly. I don't know why it did that, but we have alkanes, which end in ane, A-N-E. They have single bonds. These are examples of alkanes. We have alkenes, which end in E-N-E. They have double bonds. This is the alkene portion of the structure. This is the alkene portion of the structure. This is the alkene portion of this structure. We have alkynes, which end in Y and E. They are C triple bond C. You should have seen another line here and another line down here. Let me see if I can draw it in for you real quick. This right here is where the carbon connects with the other carbon. Okay. And so naturally what occurs is that when carbon is triple bonded, it must be in a straight line. However, it is theorized that there are alkyne cyclic structures, so for the sake of theory, we will look at those in a little bit. But they are not, because of the strain on the atoms, they are not likely to occur, okay? But we will be looking at them. So a functional group is an atom or group of atoms that define an organic family with distinct physical and chemical properties. It is the reactive part of the molecule. Reactions typically take place at a functional group. These are cyclic aliphatic hydrocarbons. They're aliphatic, remember, because they don't have single bonds and double bonds alternating. Alternating means to come repeatedly one after the other. These are all single bonds, so they are cycloalkanes. Now this is 1, 2, 3, 4, 5, so it's actually called a cyclopentaalkane. This is 1, 2, 3, 4, 5, 6. Remember our rules: penta, hexa, hepta. So this is got 1, 2, 3, 4, 5, 6. It's hexa. This is a hexaalkane, a cyclohexaalkane. Okay. Now because this has a double bond here on both of these, they become alkenes. So this is a cyclohexaalkene. And this is 1, 2, 3, 4, 5, 6, 7, 8 carbons. So that means octa. So this is a cyclooctaalkene. Okay. This has 8 as well. And this is where we were talking about theoretical activity. This is not likely to occur, especially in a 5-membered ring. Okay, because that's a lot of strain. I mean, really, these two are ready to snap, one or the other, this one or this one. And really what's going to happen is if this did exist in a transitional state, you would have like a little molecule that would come in here and attack here, or a molecule that would come in and attack here. Because these are ready to snap. It's like a rubber band. That's a very, very tight fit. And the same thing goes here. You're going to have something happen here or something happen here, because that's too much ring strain. Although they do theoretically exist, so we have to look at them anyway. So they're called cycloalkynes, okay? This has 8, so it's a cyclooctaalkyne. This has 5, so it's a cyclopentaalkyne. Don't worry about the naming. We're going to be looking at that a little bit more. We have aromatic hydrocarbons. These are also known as arenes, which are also, again, known as aryl hydrocarbons. Any hydrocarbon that keeps alternating double bonds throughout its entire structure. These are aromatic, okay? Remember, alternating double bonds to single bonds is aromatic. They are also called arenes. They are also called aryl hydrocarbons. It must occur throughout the entire structure. These alternating double bonds act like train tracks that allow the electrons to delocalize. That means to leave their local area and move around freely within the structure. Okay? So they're like train tracks. That's basically what they act like. Okay, here we have our aromatic hydrocarbons. Again, they're also called arenes or aryl hydrocarbons. Look at this. Benzene has alternating double bonds and single bonds. This is what the hydrogens connected to the carbons would look like for benzene. And it can also be written like this. This is the shorthand notation. Remember that we're learning chemistry grammar and how to draw things? Well, chemists don't have time to draw every single hydrogen all the time. So we're going to be learning to draw a lot of hydrocarbon structures today. What you're going to need to know is that for every point where there's every point represents a carbon, okay? And then to that you need to fill it up to make sure that there are 4 bonds with hydrogen. So because there's double bonds here, alternating double bonds and single bonds, that necessarily means that there has to be 1 hydrogen all the way around. Okay. Now for toluene, consider that this has 4 bonds already connected to it, so there's no extra room to put a 5th bond for a hydrogen. Okay. Now this is something called, this says orthometaparazylene. What that basically means is that this CH3 group can be connected here, ortho, it can be connected here, meta, it can be connected here, para, parallel, okay? And I just kept telling myself over again when I was remembering ortho, meta, para. You don't have to know ortho, meta, para. But if you want to pursue chemistry, you should consider getting to know what that means. If you have more questions about it, want to learn more about ortho, meta, para, talk to me and I'll help you learn how to draw. These are just alternating single bonds, double bonds. They are aromatic hydrocarbons, okay? All right, now it's time to draw and synthesize what we learned. Synthesize, remember, means to create. So we're taking what we have learned during this lecture and we're piecing it together. And we're going to be working together in groups or on the board in class. Thank you so much for being great chemistry students. I think you did a fantastic job in this unit. I'm really blown away by all your efforts. And yeah. Chem is try.